Hello everyone, this is Sudheer working as an assistant professor at Department of Civil Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to demonstrate about the Bernoullis equation, which is an important experiment and which is the heart of our fluid mechanics, the whole concept. So the Bernoullis equation states that for an ideal, steady, uniform and viscous fluid, the total energy remains constant. The total energy remains constant. So how do you define the total energy again? It is defined as the sum of pressure head, velocity head and the atom head. It is called as a total energy. Now the total energy line is the one in which it is going to obtain by joining the pressure head, velocity head and atom head. That is called as a total energy line. And hydraulic gradient line is another important parameter that needs to be considered in this experiment, and it is defined as the sum of pressure head and atom head is called as a hydraulic gradient line. Now through this experiment we are going to draw the total energy line and as well as hydraulic gradient line from this experiment. This experiment name is called as verification of Bernoullis equation. Means we are going to plot the total energy line and as well as hydraulic gradient line. Now coming to the apparatus of our experiment, here we have a source tank in which it supplies the water to the required point of elevation. Since it is at a lower elevation, we require some pump as it provides some external energy or with the help of some electrical energy in order to lift the water at the required elevation. And these two tanks are considered as the points that is at the starting of the pipe and at the ending of the pipe. So let us assume this is the point number 1 and let us assume this is the point number 2. And apart from that, we have a transparent pipe. We have a transparent pipe. Inside the transparent pipe and another pipe which is of having differential cross-sectional area. Which is having differential cross-sectional area is inserted, and that pipe has been connected to a delivery pipe or an outlet pipe, and this outlet pipe has been connected to a collecting tank, and this collecting tank is basically an essential element for all the experiments in order to calculate the actual discharge. Then another important thing which we require is about the stopwatch. So this is the one in which we are going to calculate the time taken for the level of water in the stopwatch. Now we will come back to that calculation of the actual discharge. Now coming back to the experiment, when the water is started flowing through this venturi meter, or we are going to say maybe a varying cross-sectional area, when the pump is on, the water starts flowing through this cross-sectional area of the pipe. In that case, here here you can see some joints, some points are connected. So these are called as a piezometric points. These are called as a piezometric points, and these points are connected to a scale, and this is called as a piezometric scale. We can say that this is called as a piezometric scale. So is there any rule to consider about these points? No, there is no specific rule that we need to fix the point at this location only. These points are randomly located in such a way that whenever there is a change in the cross-sectional area, that point is going to be identified. That's all. Okay. Now, according to that point, we have identified some 7 to 8 number of points, and those points are connected to a scale which is called as a piezometric scale. Now, what happens when the water starts flowing and before going into the discharge tank, that is the outlet tank, you should ensure that there should be no air bubbles entrapped. Why? Because the statement says that under a steady state flow condition. So if there are any air bubbles that are being entrapped here, that doesn't mean that it is in the steady state condition. So in order to achieve the steady state condition of the flow, the air bubbles should be entrapped. So the air bubbles we are going to remove with the help of just by operating this outlet drain pipe. So once the steady state condition is achieved, close this tank. Then once the valve is closed, automatically we can see some levels of water according to the cross-sectional areas here. According to the cross-sectional areas since as we had discussed in the earlier video of the Venturi meter, since as in the case of Venturi meter, it is having the differential cross-sectional area, and whenever there is a change in the differential cross-sectional area, automatically there will be a difference of the pressure, and that pressure is going to be noted with the help of this piezometric scale in terms of pressure head. So therefore, we are going to calculate, or we are going to find out the piezometric head at these points with the help of this piezometric scale. Okay, what is the piezometric head? Just it is the magnitude or the intensity that is obtained by dividing the pressure at that point with respect to the specific weight of the water, that is rho into g. So where rho is the mass density of the water and g is acceleration due to gravity. So here we are going to calculate directly the pressure head itself. That we are going to call it as an H. So remembering the equation of the Bernoullis equation, that is P by rho g plus V square by 2z plus Z is equal to constant. Constant means what? Under in which condition it is going to obtain again? If at all the conditions that has been mentioned in the statement of the Bernoullis equation has been satisfied, then we can say that at all the points the total energy is the same. But in the real scenario or in the real fields, we don't see the ideal fluid. Only we deal with the real fluids. Of course, again the fluids are of different type, and in here we are going to consider about only the water. Okay, so it may be of any type of the liquid, or it may be any of the gas also. Fluid may be comprised of liquid or gases. Okay, then in that case, if we are going to take the real fluid, obviously there will be some losses because the ideal fluid does not exist, and hence we cannot say exactly the total energy remains constant at all the points. Now, our main aim of the experiment is that in order to prove that they are going to be approximately equal. In terms of total energy. Where we are going to calculate the total energy at all the points where the piezometric scale has been shown here. So how do you get the total energy here? That is, it is a combination of the pressure head, datum head and velocity head. So as we are discussing, the piezometric head is directly taken as P by rho g, that we are going to directly obtain with the help of the piezometric scales. Directly some measurements are going to be taken here. Here we can see some 42.3, or here you can see here some 42.5, and here you can see 42.8 and a 40, and some readings are going to be visible here. So that the values can be taken into consideration as P by rho g directly. Then next parameter is about the datum head. Datum head is what? For example, if you are going to take the earth as a reference, that is the ground surface as a reference, and if you are going to take the center line of the pipe as a reference, since they are parallel, automatically we are going to take the Z datum is equal to 0. So in this experiment, the datum head is, or the datum is the center line of the pipe. Then where we are going to consider the datum? If at all, if the pipe is vertical or if the pipe is inclined. If the pipe is vertical or if the pipe is inclined, then we are going to worry about the Z datum head. Here, if you are going to see starting from the point 1 and the ending of the point 2, then as there is no inclination, obviously the Z datum head is horizontal, and therefore there is no consideration of the Z value here. Then only the other remaining value is V square by 2g, which is also called as a velocity head. The velocity head can be obtained using the principle of the continuity equation. So as we are very well known that whenever there exists a fluid flow, the continuity equation can be applied, and in vice versa, when there is a continuity equation exists, automatically the fluid flow exists. So based on that principle, we are going to apply the continuity equation here. What is continuity equation? Q is equal to A into V, that is the area of the cross section into the velocity of the fluid particles that is passing through the cross sectional area. Now that is called as a discharge. Now again here, our next question is, how do you calculate the discharge? As we have very well known that the discharge is the same as the of actual discharge. That is the actual discharge we are going to calculate with the only single formula, that is Q is equal to, that is the Q actual is equal to A into R by T. So what is meant by A? That is area of the cross-sectional tank, and the R is the rise of water level in this piezometric tube. Then what is T? The time taken to rise the water level for a fixed period of R, for a fixed value of R. So that is the value that we are going to obtain here. So again in this case, Q actual A into R by T, where A is a constant value. Since throughout our experiment this cross-sectional area does not change, and hence the A value is constant, and R value, that is also we are going to keep it constant, but it may be varied from apparatus to apparatus. So therefore the R value is kept as a constant value. Then only the variable parameter in that equation A into R by T is only the time taken. So how do we calculate the time taken? With the help of this stopwatch, and depending upon the pressure we are going to provide, either that is with the help of this outlet or drain valve, we are going to operate this pump. The flow, we are going to control the flow within this pipe, and hence we are going to say that the pressure is going to be maintained for different heads, and once there is a difference in the pressure, automatically the time taken to fill that gap of maybe 10 centimeters or 5 centimeters or 3 centimeters will be varied, and therefore we are going to calculate Q is equal to A into R by T. So with the help of this formula, we are going to calculate Q actual. Again, in turn, this Q actual is essential to determine the velocity head. So using the principle Q is equal to A into V, that is the continuity equation. What is meant by A here? Area of the cross section. Here you need to remember very clearly that we are going to calculate the velocity at these points, the velocities at these points where the piezometric tube has been connected. So you should be very careful in applying the formula, the continuity equation. So what is meant by A here? The area of the cross section at the duct 1 or at the point 1, and the area of the cross section at the point 2, area of the cross section at the point 3. So all these values are again constant, and it will be provided to you as an input. So once in that equation, this continuity equation of the discharge equation, Q is equal to A into V, when Q is the Q actual, that is known for us, that we are going to calculate with the formula A into R by T. And here in the another equation, A1, A2, A3, A4, those are also going to be as a constant. What is other unknown parameter here? Only V is unknown. So V can be obtained by Q using the formula Q is equal to A into V, that is V is equal to Q by A. V is equal to Q by A. So therefore, the velocities can be calculated at different cross sections. That is that all the points where we had fixed the piezometric scales. Then, like once if we calculate the V value, again we are going to calculate that B square by 2G value, which is also called as a velocity head. And once if you know the velocity head, already in our previous discussion, we have the values of the P by rho G values directly, and therefore now we have the V square by 2G's value directly. Now combine them, that we are going to get it as a total energy. So how do you obtain the total energy here? The line which is obtained by joining the pressure head, velocity head and datum head is called as a total energy. So what is the significance of the total energy line? It describes the flow pattern and also it describes the cross-sectional area of the pipe. Suddenly, for example, if you are going to remember this cross-sectional area, since it is in a gradually varied cross-section, in the similar manner, we are going to obtain the total energy line. The total energy line means whenever there is a sudden cross-section, whenever there is a sudden change in the diameter of the pipe, obviously the total energy line is also going to be dropped directly. And if there is a gradual change, then there will be a smooth curve changing its slope. Okay, so that is the importance of the total energy line. Then the other important parameter is the hydraulic gradient line. If at all, if the flow is uniform, then the hydraulic gradient line can be defined as the line that is obtained by joining the pressure head and as well as the datum head. So in this experiment, as we had taken, the data head itself is the center line of the pipe, and moreover, it is a horizontal, and therefore Z is equal to 0 again. Then the line which is joined by obtaining by joining all the piezometric values, that will be directly considered as a hydraulic gradient line. That will be directly considered as a hydraulic gradient line. So through this experiment, we had concluded finally taut energy line and as well as the hydraulic gradient line, and which describes the flow pattern in this experiment. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.